Okay, let's go to the next chapter. The next chapter is electromagnetic waves. Okay, I remember when we were working with charges. When we have a charge, let's say a positive charge. If the positive charge is at rest, remember it has only the electric field, right? The electric field, right, is present only when the object is at rest, right? Velocity is zero, right? What happens when the charges move? Imagine now we have a current, right? Right? Current in this direction, right? This is current. So we have the charges right inside, positive, right, moving, right, with some velocity, right? When that happens, we know that a moving charge, right, induces a magnetic field, right? So we have the magnetic field produced by these charges, right? Right, and this is a case when we have charges with some velocity b, right? Some velocity b, right? And in this case, we have that these charges producing a magnetic field, right? Remember, we use the right-hand rule to see the direction. If the current goes in this way, right, the magnetic field goes right in that way. Perfect. Now, what happens if the charge accelerates? That's the next point. Imagine that we connect the charge with a, let's say, spring, and we make oscillate the charge, right? We make oscillate the charge, right, with some velocity back and forth. Now we have acceleration. In this case, V is constant, right? V constant, right? Now in this case, we have acceleration. Well, acceleration is not constant. We have acceleration, right? Acceleration. Look, when the charge object, the charge particle accelerates, right? At the beginning it moves, right? So it produces a magnetic field, but now because the charge accelerates, this magnetic field is changing too, right? So it's found that at the beginning we have electric field. If we change the electric field, right, we accelerate it, right, the electric field. This electric field, right, induces a changing, right, magnetic field, correct? Now, a magnetic field also, when it changes, induces an electric field, right? And we have a change, right? We have a change. We have magnetic field, electric field, magnetic field, electric field, right? Right, and they propagate at speed of light. Can you see it? Okay, so in this case, for this picture, what do we have? We have a, let's say, electric field. This electric field, right, produces a perpendicularly, right, magnetic field. And then if this one changes to this magnetic field, changes, right, then produces, right, a electric field. The electric field still keeps changing, right, produces a magnetic field, right, and so on. This is the way how light is created, right? In that way. These two fields are perpendicular and they are self-sustained and propagate. Got it? Another way how we can see this part is we have a changing, right? A changing, right, electric field. Electric field is changing, right? So remember, a changing electric field induces a, right, changing magnetic field, correct? Can you see it? Okay, so this is a magnetic field. Now, if we have a magnetic field that changes too, so we create the same concept, right? Imagine that we have now a magnetic field that changes in this way, right? If it changes, of course, induces a electric field. So we have an electric field now induced because of the change in the magnetic field. So what we can get then, what we can get is that right here a change in the electric field, right, produces right, a perpendicular magnetic field. And the same thing right here, a changing, right, magnetic field with respect to time induces, right, or create, right, a perpendicular electric field. And this is again the electromagnetic, we call these electromagnetic waves. Later was proved, right, we know already, right, that for example light behaves as a wave and also behaves as a particle. In this section we're dealing with waves, right? So the electromagnetic waves. And these are formed by what? Are formed by electric field and magnetic field, right? Electric, magnetic field. And these two are perpendicular to each other, right? And that's what we call electromagnetic waves. Electric field, magnetic field, in that way, or in this way. Can you see it? Got it? Of course, these two are perpendicular. These two are perpendicular. These two fields are perpendicular. And one way to represent them is in this way, right? This is the direction of propagation, right? And then we have, let's say, the electric field, and also we have, right, the magnetic field. Let's say the magnetic field goes, let's say, in this way, right? So this is again the magnetic field, perpendicular, right? Let me do it better with this. Go like this, right? Perpendicular, right? Like this, perpendicular to the electric field. This is electric field, this is magnetic field, right? Perpendicular, right? These are perpendicular again to this one, right? And so on. So we create again the electromagnetic waves. It's a combo, right, of the electric and magnetic fields. A changing electric field produces a change in magnetic field, a change in magnetic field, electric field, right, and so on. And this is the direction of the wave, right? Wave propagates in that direction. Got it? Okay, perfect. Now, let's go to the electromagnetic spectrum. Okay, let's do it. Electromagnetic spectrum. Okay, electromagnetic spectrum, electromagnetic spectrum. Let's just start with visible, right? We have visible right here, visible. The visible is just the rainbow, right? When we break the visible into the frequencies, we create the rainbow. Okay, so we have the rainbow, right? The first one, let's say, gonna be red, right? And then we have orange, and then we have yellow, and then we have what? Green, and then we have what? Blue and violet. Got it? Now, what do we have below red? Below red we have infrared, and then we have microwaves, and then radio waves, right? Radio waves. Also, what do we have above? Above violet, ultraviolet, right? Ultraviolet. And then we have X-rays, and then we have gamma rays. It says gamma, right? Gamma, okay, gamma. Gamma rays. Perfect. So this is the electromagnetic spectrum. Also, because we're dealing with waves, right? When we're dealing with waves, we know that, let me make a quick introduction. We have a wave, right, like this, okay? Remember, we have the amplitude, and we have what? The time from here to here, right, is called the period, right? And the distance, right, from here to here is called lambda, right? Lambda, okay. Perfect. How do we define speed? Speed, remember, is distance divided by t. Now, when we go to the waves, right, we know that the distance is represented by lambda, right, and the time is represented by the period, okay, t. Okay, so we can say the speed of the wave is equals to lambda. This is lambda. Lambda is called the wavelength. Okay, wavelength, right? And this is the period, right? T. Also, it's known that frequency, right, is defined in function of the period as the inverse of the period. When we involve this equation right here, right, we get that the speed of the wave is equals to the frequency times lambda. The units of frequency is hertz, right, and the units of lambda is in meters. Okay, great. So we have that the speed of the wave is equals to frequency times lambda. Okay, now let's see what happens when we involve, right, the wavelength and frequency to represent, right, or to relate them to the electromagnetic spectrum. If this is the visible, imagine this is the red, right, the red wave. It's gonna be the violet, right? It's gonna be the ultraviolet. It's gonna be the X-rays. It's gonna be the gamma rays, right? And we're going down, and the wavelength increases for the infrared, right? For the microwave, right? And from the radio waves. Radio waves. Got it? So this is again the electromagnetic spectrum. In this case, look, the frequency, because the speed of light is constant. Let me go to that part, right? The symbol for the speed of light, right? Right here is for any wave. Right here is for the speed of light, right? The special case is equals to the same thing because a wave, right? Frequency times lambda. But this speed is constant, right? So it's gonna be about, right, speed of light about 3 times 10 to the 8 meters per second. It's constant, correct? Now, let's see what happened. If we create this table, let's say instead of 3, let's use 30, right? 30 is equals to, let's say, 1 times 30, right? Or equals to what also? It's equals to 2 times 15. Also equals to what? 3 times 10. Or equals to what? 5 times 6, right? Or equals to what? 6 times 5, and so on. We call this the speed of light, right? This is gonna be frequency, is gonna be lambda, these factors, correct? Okay, great. Now, if the frequency increases, right, the wavelength decreases, right? Like in this picture, right? If the frequency increases, right, the wavelength decreases, right? This is the wavelength lambda from here to here, right? If the frequency increases, the wavelength decreases, correct? So again, that happens because the speed of light is constant. Okay, great. Now let's go to the energy that is carried by an electromagnetic wave. Okay, let's do it. Okay, so let's go to energy. This is a very important quantity, right? Energy must be conserved, remember? Energy is conserved, that's why it's important. Okay, energy carried by energy, right? Energy carried, right, by a electromagnetic wave, right? Electromagnetic wave. Okay, this is coming from the concept that we had before, using the energy stored in a capacitor and also the energy stored in an inductor. It's found that from capacitors, right, from capacitors, the electric energy density, right, electric energy density, right, is defined as the energy per volume, right, is equals to, equals to energy per volume, right? And it's found in the chapter for that section of the chapter, right, that involves capacitors, right? It's found that this is equals to 1/2, right, epsilon naught the electric field square. This same thing happens for using inductor, right? This is from inductors. From inductors, we have the same thing, right? That the magnetic density, right, is equals to the same thing, energy, magnetic energy, right? Energy divided by volume, and in this case is equals to mu naught, right? It's a constant already given, right? The same thing as epsilon naught, right, times the magnetic field square, right, divided by actually it's gonna be this the other way, right? It's gonna be v square divided by 2 mu naught. Correct? Now this is the energy stored in a capacitor. When we have a circuit, it is transmitted to, right, through an inductor, right, and the energy must be conserved, right? The same thing as the energy density. So because energy must be conserved, these two must be, right, the same. So in that case, we have that 1/2 epsilon naught, right, E square must be equals to B square over 2 mu naught. Again, this is because energy must be conserved. Wait, now from here, what do we have? We have that the electric field, right, is equals to the magnetic field divided by the square root of epsilon naught mu naught. Right? This is one of the most important results that we get, right, when we are dealing with electromagnetic waves. It's found by Maxwell, right, that this quantity is actually the speed of light, right? The magnitude is just the speed of light, right? So the speed of light is found to be equals to 1 over square root of epsilon naught, right, mu naught. Correct? That's the speed of light, the magnitude, right? And because it's coming from these formulas, right? The conclusion is that light is an electromagnetic radiation, right? It's part of the electromagnetic spectrum. Got it? Okay, now let's go to the next topic. The next topic is gonna be intensity, right? Let's go to intensity. These are constant, are given, right? These constants in books, right? Are given. So we apply the constant right there, and we get the answer, which is the speed of light. Okay. Now let's go to the last topic for this lecture. The last topic is gonna be intensity. Intensity, right? Intensity. It has different symbols, right? We can use I for intensity. Now for this lecture, let's use S, right? S for intensity. Okay, and the intensity is defined as the power, right? Power is the power of that passes perpendicular through a surface, passes perpendicularly, right, through a surface, right, through a surface, right, divided by the area of the surface, right, divided by the area of the surface, correct? So the intensity then is equals to what? Power divided by the area. Power passes perpendicular, right, an area divided by the area, or perpendicular as surface, and then divided by area. Okay, but how do we define power? Power is just what? Energy divided by time, right? Power, remember power, right? It's just energy or work, right? Energy divided by time. So when we involve this definition right here, what do we have then? The intensity is equals to energy. Remember I dealt with energy before. Energy stored in a per unit volume, right? Energy divided by time times, right, area. Correct. That's gonna be the intensity. So we create a new unit, right, or a new quantity, because it's a new quantity, because we divide quantity by another quantity. So we create a new quantity and we define it as intensity, right? So it's a new quantity, it has unit, right? So what should be the unit? The units of power, right? Gonna be joules, right? Joules? No, watt. Gonna be watt, right? The units of area, meters, right? Square, okay. Meters square, correct? Okay, those should be the units of intensity. Okay, great. Now let's see what happens when we're dealing with both, right? We're involving the energy, right, per unit volume, which is the energy density. Okay, let's do it, and let's apply that definition right here, because right here we have energy. Perfect, right? Great. So we found, right, that the unit, the total unit density, right, is equals to the energy in the capacitor plus the energy, right, in the conductor, right, or in the inductor. So we have equals to 1/2, right, epsilon naught E squared plus, right, magnetic field squared divided by 2 mu naught. Correct? This is the energy stored in the capacitor, the energy stored in the inductor. So the total density, right, is gonna be the sum of these two. Correct? Perfect. Now, how do we define this? Because these two are the same, right? Must be the same. This convert into this, is converted into this. So we can also say that the total, right, is equals, if this is the same as this one, so at the end we have twice this one, correct? So at the end we have epsilon naught, right, E squared. Correct? Now, let's see what happens. How do we define this energy density? It's going to be energy, right, per volume is equals to epsilon naught, right, E squared. From here, energy, because we're dealing with energy right here, right, energy, right, equals to volume times epsilon naught, right, E squared. Correct? Now let's find this energy. Okay, we can find the times is provided, right, area, but now see what happens to energy. What happens when we involve energy right here for the intensity. Okay, let's do it. Okay, let's do it. So then we have that intensity is equals to what? Energy per watt. Okay, energy, which is what? Volume epsilon naught E squared, right? Usually when we're dealing with electric and magnetic field, right, we go to the electric field. That's the most important one. Everything is coming from here, right? This magnetic field is created when we change the electric field. So this is most important than this one is. This is the original one, let's say, the electric field. That's why I usually use as a reference the electric field because of that. Okay, perfect. So divided by what? Divided by times the area. But when we have, right, the electromagnetic radiation, remember, we have the field, magnetic, right, electric, right, the magnetic, remember, and electromagnetic waves. Imagine now we have this volume. Let's try to collect, right, the energy in this volume, because volume is involved right here, correct? Now this is the area right here, and we have this distance, right? Because the waves travels at the speed of light. Remember, speed of light, c is equals to for any speed, right? It's equals to what? Distance divided by the time. What should be then this distance according to this formula, where that distance is equals to ct, correct? Now when we involve, right, now volume is equals to what? Volume is the area times this thickness, right? That's the volume for this segment, right? Okay, perfect. And then volume then is equals to, according to this, area times d, but it's gonna be ct. When we involve this value right here, what do we have? Well, the intensity is equals to area, right, ct epsilon naught, right? This is t epsilon naught e squared, right, divided by ta. ATA is cancelled, and what do we have at the end? At the end we have, right, the intensity of this wave, right? Let's see, of this radiation. So intensity is equals to c, right, epsilon naught, correct, b squared. Well, we can use this one. These are the same, right? In this picture, this one or this one, the meaning is the same, correct? Okay, maybe you like this one. Perfect. So let's use epsilon naught. Okay, epsilon naught like that, correct? Now that's the intensity that is used, right? Mainly, we have another one, right? When we involve the magnetic field, also we can say that the intensity is equals to the speed of light, right? V squared over mu naught. Okay, again, mainly we use electric field because it's the most important one. We have it on the electric charge, right? Positive, negative, right? And the magnetic field again is produced when the charge is moving, right? And then we have the magnetic field. Correct? Okay, let's start right here, part 1 for this chapter. Now let's go to the next chapter, which involves polarization, right, using light. Okay, see you in the next video.